to the call. So in this session, we are going to talk about linear regression. So as we said earlier, in the first lectures, we discussed in general what is Scikit-Learn. In general, what is Scikit-Learn? We kind of do a little bit comparison with the TensorFlow. And we say TensorFlow normally is good for neural network, deep learning, etc. And also unstructured data here. We say Scikit-Learn is good for structured data or classical machine learning problem like decision tree, regression, etc. Now, in this section, we are, as we said earlier, we can't go through all the machine learning, I would say machine learning steps. But one thing we can remember we said in a previous slide, Scikit-learning is very consistent. The steps you take for decision tree, most likely the same step you are going to take for neural network support vector or the supervised learning. A little bit difference. And of course, the name of the packages or the functions are different. Yeah. So let's see the linear regression. Yeah. If no question, let's see the objective first. So the objective here, hopefully, by the end of this class, we are going to understand what is linear regression. And linear regression, again, is a supervised machine learning algorithm. To be more specific, it's a regression also. And Scikit-Learn support it. We have package for linear regression. And it works like you train first, you predict, then you evaluate the regression. And that's the steps we have. And I'll say that most of all the supervised learning, that's the step. Train, actually first you have to, of course, make sure your data is clean. So we do the data pre-processing, normalization. If we have to change the discretize. Now, I always mention discretize. What discretize means, for example, I'm doing, let's say, classification of age and the age of the students. No, even let's say we're doing regression of age and the age of the students are from 1 to 100 years. Doing regression for age, like it will work. But why can't we change the age and we do it more or less like a classification? So we are going to discretize the age from numerical to, again, a concept like more like ordinal or nominal. Then I'll say ordinal. So the age from 1 to 10 is 1, 11 to 20 is 2. That's one option if the target variable is what we want to convert, discretize. Also in the process, we may say that, oh, okay, say the ages are too many. Our target variable is different. Age is one of the input variables or the attribute. So we can stay discretize. So we can discretize any variable, whether it's an input variable or output variable. Yeah. Or independent variable or dependent variable. Kind of regression takes us to statistics. So we're trying to use some few statistics terms here. So if no question, let's move on straight. So what is linear regression? Here we see a linear regression. First of all, I would say it's a model. It's a model that predicts continuous numerical outcome. So here we say supervised learning. First of all, it's a supervised learning model. Oh, algorithm. Actually, let me use the term algorithm. It's a supervised learning algorithm, and it's used for predicting continuous numerical values here. It normally models the relationship between what independent variable, which will be our x's, and also the dependent variable. Now, if we say simple linear regression, it means our x will be only one value. Let's say, for example, I'm using the age to predict weight. Or I may use age and another variable. Let's say we have two variables, two or more variables to predict y. In this case, we will call it a multiple linear. Now, if the, we are assuming we have a linear relationship. So if the relationship is linear, then it's a multiple linear regression. Why is it multiple linear regression? Because the independent variables, they are more than one. The concept is the same. The difference between simple linear regression, multiple linear regression is the number of independent variables we have. So that's all we can mention here. Let's see if any question. And as we said earlier, linear regression is borrowed from statistics. It's been around hundreds of years before machine learning. So it's a statistical method used to model a relationship between, again, dependent, which variable, which would be the target, and also what? One or more independent variable, which would be the features. Simple linear regression, as we said, you have only one feature or one independent variable. Multiple linear regression means you have more than, it can be more than two, any amount. Yeah, and mostly in the real world, very rare that in a real world situation problems, it's very rare that only one variable will predict an outcome. Most likely to be a lot, combination of a lot. Uh, then there we have to consider the concept of multi-coloniality. Sometimes you may have S1, S2, but S1 also predict S2 or S1 determine S2. We don't want that. We want S1 and S2 both to be determined. Yeah, or they both work together to determine why. Yeah. Okay, so let's see. Let's keep going. Why linear regression in data science? Well, first of all, they mentioned they're simple and also very easy to interpret. So simple and interpretability baseline model. Also very fast to train and easy to, again, implement. Yeah. Simplicity. Speed is very good too. And the outcome is very straightforward that even a layperson will understand their concept. Also, I would say it's also benchmarking the complex models. And it's very common real world, like example, giving you business forecasting, healthcare analysis, economics, and finance, even medical risk scoring. See, we are using the term scoring called linear regression predict numerical value. In terms of finance, maybe we predict the money, unless it's stock price, etc. Yeah. And also it can serve as a foundation for advanced model. As we said earlier in a machine learning or data science program, always start with a very simple model, see what's going on, then come with a complex model, see if it will improve the score, evaluation score, maybe to work more better. Let's say the accuracy for linear regression gives us 76%. Then I use let's say support vector machine also is an equation, numerical I can work for. And I use support vector machine, I get 90%. Of course, I will keep the support vector machine. But if I use vector machine, I get less than 70 or less score than linear, which is simple, then maybe I'll just keep my linear. It just happened that the type of problem and the type of problem depends on the data. So the type of data, linear model even is very simple, but it works better than support vector machine, which we thought is the most very powerful. Yeah. So again, it depends. So the goal here we say serve as a foundation for advanced models. Now, linear regression intuition. First, we want the best fit line. And also, linear regression is so common that even Excel, a common Microsoft Office Excel, have the features, everything for us. It's very common in almost all the statistics applications. Which one we can remember again? Minitab, or and then they all have regression. SPSS have. Actually, SPSS is very complex. You can get a package for neural network, everything included in it. Yeah. Or JSP, very good one too. Is it JSP or JS? Yeah, JSP, JSAP. No, JSP. Yeah. Actually, I have that application here. Since we have time, let me see. But again, this is Python class, so it doesn't matter. We are not going to use any application, but just to show the example. I use JSP a lot for another class I take. I think that's it here. Yeah, JASP. Yeah, JASP. I don't have to use it now because this class we are not using anything except Python. So Python. Yeah, so yeah, that's the whole idea. Find the best fit line through the data points. A best fit line means hopefully our total residual will be zero. Or most of the time is in real world it's impossible. Now you can see that regression is like college algebra linear equation. It's almost the same, but the simple way because linear equation, all the lines is all the points are on the line. So you just find the slope, and that will tell you the thickness of the line. But in the real world problem, you can't get all the points on the line. So a best fit line means the line that most of the points are close to. Technically means the total error or the residual will be lesser. If the points are far away from the best fit line, then the error will be very high. So it's not the best fit line. So that's all I would say here. Also, the model learns coefficients, the coefficient that will minimize the prediction lines. That's the concept of sloping now. We'll talk about that. Also, error is measured as a distance between what, as we mentioned earlier, residual. Error is same as residual. The difference between the actual value of the output, the training data actual Y value, and the predicted Y value, the difference of the two. The goal is that we want to make it zero. Then we have a perfect system like college algebra and linear regression. Yeah. So that's all I can say here. Now, Scikit-Learn solve this using again numerical optimization. The function everything is given to us. Our goal here is to select the training and the test data. The rest is done by Python. So that's why Python is good. We don't do any programming here. Okay, so yeah, this is the whole idea. Now we come back this. Yeah, we mentioned this before. Simple linear regression, y equal to b0 plus b1s. You could take us to statistics. This means we have only one value for x, the independent variable, and b1 will be the slope. b0, we call it the y-intercept. Y-intercept is when s is 0. What's the value of y? Then when you have multiple linear regression, well, here you can see, we say from s1 to xn, it can be any number of x. Each x value have its own slope. So b1 is 1, b2 is 2. Yeah, so that's, yeah, b1 stands for intercept, and bi can be b1 to any, is the coefficient. Yeah, they call it coefficient weight, but same as the concept of a slope also. Okay. So linear regression as a machine learning, yeah, we say it learns the parameters from data. So this is not a hard coded rule. It's very straightforward. The parameters. What are the parameters? Of course, that's actually the slope is very important. Or the coefficient. Let me use the term coefficient. So the training involving also adjusting the coefficient automatically. We feed in the label data. This will be our training data. We have the S values and the target together. The system or the adjusting coefficient automatically to get the best fit line, which means to get the model that will give us less error. Yeah. Okay, so now we come to how we can use so that's the fuse, just a little bit theory of regression, linear or multiple regression. Now we come to how Scikit works. So yeah, so the first thing we can mention here, as we can see, also, as we said earlier, the errors are very important. So sum square error normal will be the difference of sum square error means you sum squared error. So the difference of each error, all square, you sum everything. So if the data set is 100, we are going to get 100 errors. We sum each error before we square. The reason is the same as variance. If you find a total deviation in statistics, it will give you 0. Because the difference of actual value and the mean, or you add, or it will give you 0. So that's why we squared the deviation. That's the difference between each value and the mean. If you don't square and you add all of them, because some of the value will be greater than the mean and lesser than the mean, they will cancel each other. The total will be 0. So you square them. The same concept here also. Most likely some of the errors will be above or below the best fit line. So you square each one, they sum. So we have a sum square error, mean square error we saw in the previous lecture slides. Yeah, so now let's start with the introducing Scikit-Learn. Yeah, we say, of course, that is the popular, we already went through popular machine learning for Python. and also ready to use machine learning algorithm. We mentioned it's very consistent API for training and prediction. Linear regression also is available. That's our first concept here we are going to mention. So this the same again consistent process. Same concept. So you get your data, you train, you get your model, evaluate it. And we'll go through the steps. So we mentioned about fit, function, predict function, everything is here. So here, we have sklearn.linear_model. Now, Scikit-Linear regression workflow, this is the steps again. In one more time. Now, here we are writing the code. So we said earlier before, first thing we have to do, import the library files you need. Or the library. Maybe if I would like to plot a graph or something. So maybe I can even import the visualization, matplotlib, or Seaborn, any library you think. Or maybe I may need a NumPy for the data, tend to arrays. Import all possible libraries, including the linear regression model library file too. Then the next step, we load and prepare the data. After we load and prepare the data, we split the data into training and testing. Now we have our training and testing. That's where we use the fit. Create linear regression model. Fit. After you get the model, do your prediction, then evaluate. So this 7-step is like same as writing the code. I say writing the code, the steps, same. If we don't say it today, we will say it next week. Next week, special for library, class library works that we're going to do. Oh, okay, so we have some example here. So importing the required library, as we said earlier, because I'm using, I want to do linear regression, doesn't mean I can't use pandas. You can still use your pandas. We say the Scikit-Learn is built on top of pandas, NumPy, math. Here we don't have the visualization, but if I think I need it for graphs, I will include it also. So we have the pandas, we have the NumPy. Then we have from sk.model selection, we are going to import. This is very important. That will split our data for us. So it's called a train test split. And we'll see the steps. Then also from the same sk.linear model, we need linear regression. That's our goal. After that, we need evaluation from sklearn.metrics, import mean square. So we're going to do mean square and also R square score. Or I'll say R2 score. So yeah, let's wait for a few seconds. Now, it's up to us what I'm doing. I may add more library. Or maybe I don't need NumPy, I'll remove it. Pandas, I don't need it, I'll remove it. So, now what we're trying to say here, import the library files that you think you need. Yeah, but I would say this is the best. At least maybe we're going to use pandas for checking some data preparation and then the missing value. Or actually we want to even use the data frame. Or NumPy want to use it. So it's up to us what we are doing. So let me wait for a few seconds, see if this section is okay, especially those of us who has not seen this before. Most of the time when I'm teaching this class, I would say 90% of the class, so far having get one, some of you will ask me a question that's supposed to be next week, or the solution is supposed to come in a few minutes to come. So please don't ask me questions. No, but it's okay. You can ask a ahead question also. We will explain that. As far as the question is related to what we are doing now. Okay, quiet means no question. Let's move on. Okay, so preparing the data set. You can see first thing we say we need our X and Y. If it's multiple, then maybe we need more than one X, but the target variable is always 1. And also it must be numeric. That's what we are saying. Ordered. Yeah, we are doing mathematics. y equal to, let's say, b0 plus b1s. We are doing plus and multiply. b1 times x. So all the data here is mathematics. That's why they say data must be numeric. No missing value. Now it depends. If we think missing value is less than 5% of the whole data set, where we have over thousands of data set, 5% won't make much difference. You can leave it. Or you can have a default value to be put in this. Let's say the mean of that column. Or use the panda to do something about it, set some default value. So that's all to us. Yeah, so that's the first requirement here. This is why I like this slide than the previous slide. It doesn't really explain. Even the book, it doesn't tell you. It just gives us the code. So we have to understand the code. But yeah, I think I like the way we had it now. We know what S is, what is Y, what they have to be. If we understand that, then this is the code. So you see, we are using DF. That means we are using the data frame from Panda. That's why we import it. So we have feature 1 and feature 2. Okay, so this is multiple regression. Then Y, as we said, always have to be only one variable. The predictor, the target. So if no question, let's move on. Or let's meet with, actually, this is the part of the objective of the course. The theory, if you take CS655, sometimes we have students, they have already taken the CS65 machine learning class. So what I'm saying, in terms of theory, they know everything already. But our goal here is the Python, the package, how to use it. That's the goal of this course. And the goal from week 1 to week 15. This is the, what will I say? There's a term they use. This is the main section of this is the main objective of the course. Yeah. Okay. So if no question, let's go. Okay, we got the features now. We got our package. So we need to get our spread now. Not only the package, we're using the DF also. So we got everything. Data frame. Now we have to do our training test spread. They say, we mentioned this in the theory. Be careful overfitting. Make sure the data is balanced, not imbalance. Balance. So, train test spread, first thing we should think of, how to prevent overfitting. Let's wait for a few seconds if it's okay. Then, if everything is okay, we test the model on unseen data. Yeah. So sometimes we can do simulation here. We can simulate the real world deployment. Let's say we can say the test size is 20% or 0.2. This means 80 by 20. 80 is training data, 20 is test data. You can, so for example, we have the S train, S test, Y train, Y test. We assign the train. This is the function, and this is, so I can change this to 0.3. You can change it to anyone. Now, I see here we are using the random is more better. We say it's efficient. So we are using random state, and we set it to, again, 42. And this section, we can always adjust the adjust the parameter. We can make it 0.3 anyway. If it's 0.3, that means we are saying 70-30. Random state is important. That's like, I would say, reproducibility. Later on, we can even include a cross-validation. So let's say cross-validation, I don't know, but we can do that also. Let's see if it's in this slide also. Wait for a few seconds if any question. Again, this is the main objective of this course. So we go as slow as possible. The theory, if you have a question, as I said earlier, you can ask. But I assure you that you will learn a lot of theory in machine learning when you take the machine learning class. Here, if we say we are going to discuss the theory, we can't even reach what we can't talk about packages anymore. We don't have the time. Okay, next is creating the linear regression model. So we got a linear regression function assigned to the model. So far, no learning happening yet. There's no learning yet. Yeah. If we like, we can use the ordinary least square. I think ordinary least square by default. Also, we can find a way to handle the multiple features. Can handle multiple features automatically also. Now, circuit, see here we are selecting all the possible features, everything. When we run the program, Scikit-Learn will compute all the coefficients, handle the multiple, everything for us. Our goal is you make sure we have the right packages, right functions for the right functions for the right work. Yes, for the right for correct function for the correct task. Yeah. So this is where we train the model now. So it's a model.fit. We have the S train argument with the Y train. And this will learn the interception, coefficient, all the parameters will come into play automatically. Yeah. Dot fit, very important. It's where the learning happens. Dot fit. So we remember we said fit function, predict fit, fit function. This is where we do the learning. Model will compute optimal coefficient. Training data must include by this time we already have the training data, include the labels, everything. Training data. Again, one thing, training data does not guarantee good performance. I think we mentioned that earlier. Yeah. So wait for a few seconds if it's okay. Okay. Now making prediction. We talk about predict function. So fit and predict. This is where the argument now is the test data. Test data means we have the features, but we don't know the outcome. Now it's the model have to do that. So output predicted numerical values of we said that already regression, but also can be compared with actual. But this is when we get to the evaluation section also. So the predict function apply the learning parameters. And always, as we said, the output is continuous. A continual value, numerical value. So what we are doing now, we are applying the learn coefficient to new data. You see, when we do the building the model, we are going to get something like y equal to 6.7 plus 0.8 times x1 plus 0.9 times. It can be any value. I'm just saying like multiple regression. So now when we put the test data, it will give us the value of x and x1, x2 is there. So you put it inside and it give the calculation what will be the answer for y. So here what I'm trying to say is that we are using the slope or I've said coefficient with the intercept. If you know the intercept and you know the coefficient of each value from the training, then we can predict. And that's what we're doing here. Then from here, we do the evaluation. Now, let's see. See, we are looking for the mean square error. So these are the common regression metrics. We can use mean square error or root mean square error or R square coefficient of determination. We don't need to write the function. Everything is given to us. So you can see mean square error, take your Y test, then Y predicted. And then it will do all the mathematics for us. Same thing with the R square, or I'll call it R2. It should be R square score. It take the Y test and Y predicted, and it give you the results. Remember, if R square is 1, oh, that's perfect. 0.9, good. 0.2, not too good no more. So, yeah, it's like finding the R value to find a correlation between S and Y. Normal correlation is only one variable at a time, one X and Y. So if the R is 90%, it's good. If it's 100% 1, that means all the points are perfect. They are all in the line. Then, so now when you get R value, then you square R. This is doing manually with statistics concept. But again, Python do everything for us. So the goal for us now is to understand what is mean square error, what is root mean square error, why we are doing R square score, what the score would do for us. Based on the score value will be always again actually square and also correlation normally 0. We can get negative value. Let's say if I'm looking for R, I think it can not I think sorry, it can be from -1 to +1. So when R value is negative, it means we have a decreasing order. When S increase, Y decrease, or when S decrease, Y increase. But R square value is always positive. Because we can see if R is -2, -2 square is positive. Yeah. Okay. So let's keep going. So we finish everything. We do what we have. Now we want to interpret the result. As we said earlier, if you have a low MSC, that's actually we want 0. 0 means the system do perfect because the predicted and the actual outcome, they are the same. So perfect. But always we want it to be low. We don't want it to be big. Also, R square we mentioned, if it's close to 1, or if it's 1, too perfect. R square value always from 0 to 1. 0 means, oh, you did very, very bad. Then not even working at all. No, none of the variable have any effect. Then coefficients show the impact of each feature. Kind of, I'll say, slope on the prediction. Yeah, then yeah, intercept coefficient. So these are some few rules about the assumption of linear regression. If it's a simple linear regression, we don't need to worry about multicollinearity. Multicollinearity means you have multiple x values, s1, s2, s3. And one of s1, s2, one can even determine s2 or s2 can determine s1, s3. So you have to be careful about that. There are many ways we can identify it also. Simple way you can test each other with the y or within themselves. And the value of r, actually this one, just look for the r. If r is up to 1 or close to -1, then there's a relationship between the two variables, or association between the two variables. Also, we need to consider constant variance. Now, this is take us to math statistics. Excuse me. Oh man, I'm doing good, almost finished. This recording almost no. Now, linear regression is a parametric testing in statistics. In parametric testing, we consider the normal distributed data. No, we have non-parametric. For example, I mentioned correlation. We have PSC correlation. PSC correlation means we have to test normality, normally distributed. We also have a Spearman correlation. Spearman correlation. Spearman correlation is non-parametric. It depends on ordinal data. And there's a different ways of doing it. Again, statistics, different formulas altogether. And also, so that's now even in non-parametric, majority of all the testing, regression hypothesis, everything, Spearman, they are all ordinal data, except one, which is the chi-square. I think chapter 6 maybe we went through a little bit of that. Chi-square is only based on accounting expected number. So chi-square, the variables can be nominal. No, not can be. He is nominal. Yeah, that's the only non-parametric testing where we use nominal. Majority or we use ordinal. Yeah, so just to mention the concepts here because of normality. Yeah, so the valuation of these three or four can affect the accuracy, the model accuracy. And also here we are doing linear, so linear relationship. Logistic regression is non-linear. Yeah. So advantage and limitation. Here we say the advantage, but we mentioned this earlier, simple, interpretable. It's more than 100 years old. It's been doing, we'll be using it a lot in statistics. Also, as we saw, fast training, just the function, the coefficient and intercept, the parameters determine, and works well with small data set. That's the difference between statistics and so somebody has, some time ago I was teaching statistics class. What's the difference between statistics and data man? It seems like they're almost similar. The major difference, actually with data science also, the major difference is that statistics, all the testing, both parametric, non-parametric, differential statistics, they use small data. They take sample, hypothesis, t-test, ANOVA, everyone. They use some. So regression is a root of statistics. So it works well if you have a small data set. But again, we talk about the limitation. This is linear relationship. So assuming linearity. Sensitive to outline, yes, because you are doing mathematics there. A very small and big value can have effect of the outcome. And poor performance on complex patterns also. Yeah. Actually, if you have a nonlinear, you can use this relationship distribution, you can use. Or distribution is not normal. Maybe you can, but again, that's what we said earlier. It won't give you a good model, good accuracy. You can, let me go back. You can evaluate any of these rules. So far, you are predicting numerical value or the values are numerical. It will work. But the question is, did you get a good model or the accuracy value is it high? Maybe use a neural network or support vector machine. You may get higher. Support vector machine is perfect because it works for nonlinear, it works for linear also. Yeah. Okay, so let's keep going. Okay, so we mentioned advantage and disadvantage. When to use linear regression. Target variable must be numerical, continuous. Relationship must be linear. Interpretability is important, very straightforward. Avoid data that is nonlinear, of course, because this is not a nonlinear relationship. Also, strong interaction effects may exist. And that will be the conclusion. So in this section, this slide, we learn about linear regression, not in terms of statistics, but in terms of Scikit-Learn, Python, how we use Python in linear regression, which is again a data science work. So we saw the prepared data. Actually, the example here is just to show us the benchmark or the framework for doing it. Hopefully next week we'll do the lab work. We can even use the Python missing handling functions, everything inside. Hopefully we'll see that next week in the lab. So let's wait for a few seconds if any question before we take a short break. Okay, so it's not no question.